Hey, this is Miss Laffin. Today I want to talk to you about carbon. When we talk about carbon, it's one of the most important elements that we can look at when we're talking about biochemistry, which is why I'm taking time out to talk to you as much as I can about carbon and why it's important. So the first thing I want to start with is atomic structure. All right, so carbon comes from the periodic table of the elements. So if we're looking at our periodic table here, here's carbon right over here. And you should be able to Google or have a copy of the periodic table of your own to kind of reference. Want to take a quick note. The periodic table is not something you need to memorize. It's not something you need to know back and front. Rather, it's a tool. It's kind of like the dictionary or your calculator. It's something that you can use to come up with an answer. So today, I'm going to teach you about how to use this periodic table to come up with an answer. Okay, so let's focus on carbon. Okay, all the information that I'm going to write down is going to be from this little box where carbon is located. So since this is a little tough to see, make sure you have a periodic table handy so you can be copying down that information as well. When we talk about atomic structure, there are three parts of the atom that we need to know. We have what's called a proton, we have what's called a neutron, and we have what's called an electron. Hopefully you've heard these terms before. There's three different things you need to know about each of these pieces. Number one, a proton has a positive charge. An electron is the one with the negative charge. A neutron, it actually gets that NEU from being neutral. It has no charge. Both of these are located in what's called the nucleus of the atom, while the electron is outside the nucleus, circulating in what's called an electron shell. Okay. Finally, the last piece we need to know is each of these has a mass of 1, and we call that 1 atomic mass unit. Okay. And that's going to be important. A proton has 1 atomic mass unit. A neutron has 1 atomic mass unit. The electron, on the other hand, we'd say that it has no mass. Electrons are so tiny and so small that they really don't have enough of a significant mass to contribute to the overall mass of your element. Okay, so now if we look at our periodic table, we get carbon, which is the name of our element. Its symbol is C, and the symbol can either be 1 or 2 letters. Side note, when you're writing symbols, the first letter is always, always, always capitalized. If there is a second letter, it's always, always, always lowercase. Carbon has an atomic number of 6 and an atomic mass of 12.011. So what does all of this mean? This is our atomic number. This is our atomic mass. Well, when we look at this atomic number, atomic mass, they mean specific things. Your atomic number is equal to the number of protons present in your atom. So if carbon has an atomic number of 6, that means that there are 6 protons in every single carbon atom. Your atomic number will never change. If it does change, you've then changed the element. So let's take a look at our periodic table. I've already told you that carbon has 6 protons. Well, what if I had an atom and I added an electron? That would take us, or I'm sorry, added a proton, not an electron. If I added a proton, that would make that element then nitrogen. I would have 1 atom of nitrogen instead of having 1 atom of carbon. So if I change the number of protons, if I change that atomic number, my element changes. The other piece that I have, my atomic mass, well, that's equal to my number of protons plus my number of neutrons. And that's a formula you need to know. So when we talk about our atomic mass on the periodic table, it gives us this 12.011. You might be thinking in your head, but Miss Laughlin, you said that protons and neutrons each have a atomic mass number of 1 each. So how are we getting this point? Well, this point is actually an average because you can't change the protons in an atom, but you can change the neutrons or the electrons without changing what that element is. So what this number is it's an average of all of the different types of carbons there are out there. This is the average mass. What you want to do is you want to take this number and round it. So for carbon that we're working on in class, the atomic mass would be 12. Okay, so down here at the bottom of my paper, I know that my atomic mass for carbon is 12. I already know the number of protons that carbon has because I told myself that my atomic number is my number of protons. So if my atomic number is 6, I know that my number of protons is 6. So my atomic mass equals my number of protons plus my number of neutrons. And that is what I would have to solve for. So 6 plus what gives me 12? I know that my number of neutrons has to be 6. For the purposes of our class, you've now learned how to find the number of protons and the number of neutrons. What I'm going to tell you for our class is our number of protons usually is going to equal our number of electrons. Okay? Moving right along. I've also told you that your periodic table, we're going to come back to this, is a tool. So how else can you use the tool? Well, we just learned how to use your atomic number and your atomic mass to determine the number of subatomic particles in an element. I'm also going to tell you that you can use the column and the row that your element is in to determine more about the structure of that atom. So first, the column or the family is going to tell you how many valence electrons it has. So let's talk valence electrons. Sorry. The way your atom is built, there's a bunch of different levels or electron shells that your electrons could be in. They're kind of like egg cartons. If you have an egg carton that has 12 spaces, it can only hold 12 eggs. It can't hold 14 safely. It can hold fewer than 12. It could hold 1, 2, 3, 4, so on and so forth, but it can only hold up to 12. Your valence electrons located in the electron shells are the same way. So if I look at carbon, which has 6 protons and 6 neutrons, and that's going to be in my nucleus, I'm going to start placing electrons in electron shells. My first electron shell can hold up to 2 electrons. My second electron shell can hold up to 8 electrons. Okay, so on and so forth. There's what's called an octet rule. And what you need to know from the octet rule is the number 8. Generally, your electron shells are going to hold 8. All of your elements are going to want to get to 8. So if you're ever in some advanced bonding situations, you want to remember this octet rule. Everything is trying to get to 8. It either wants its shell to be completely full or it wants the shell to be completely empty. It doesn't want an in-between state. So let's take a look at what this means for carbon. We know that carbon has 6 protons, 6 neutrons, and 6 electrons, which I already explained earlier in the video. So if we're looking at how to draw our structure, in our nucleus, we would have 6 protons and 6 neutrons. In our first shell, remember I said you can only fit 2 electrons. We have 6, so we have 2 to put in that first shell. Now we have 4 more electrons to place, so they're going to go in that second shell. This is going to be the outermost shell of my atom. This is what's called the valence shell. These electrons found in the valence shell, these valence electrons, are the ones that are going to be used for bonding. So when I bond carbon to oxygen or hydrogen or nitrogen or phosphorus, it's going to bond with the use of these valence electrons. We see from our drawing here that carbon has 4 valence electrons. So how can I get that information quickly without having to draw out every single atom? Well, if you look at your periodic table, like I said, this has to do with families or the vertical columns. Carbon is in column 14. If we take that 1 off, we can say that carbon is actually in column 4, which means it has 4 valence electrons. So if I looked over here at chlorine, how many valence electrons would chlorine have if it's in family 17? Well, again, I would take the 1 off. I'm left with the 7, so chlorine would have 7 valence electrons. Over here on the other side of things, let's look at calcium. Calcium's in column 2. If calcium is in column 2, that means it has how many valence electrons? That's right, 2. So the column will tell you how many valence electrons something will have. Your row will actually tell you how many shells that specific element will have. So carbon is in row number 2, so it should have 2 shells. If I go back to my drawing, here's my nucleus, first shell, second shell. 2 shells, 4 valence electrons, and I can get all of that information from my periodic table. The important thing is carbon and its 4 valence electrons, this is what makes carbon so very important. This is another type of drawing. This is called a Lewis dot drawing, and this shows the 4 valence electrons. Now, when you're looking at these Lewis dot drawings, you want to get up to 8 because of our octet rule, but they're kind of loners, these electrons. They don't want to hang out too close together. And in fact, until we get at least 4 of them, they don't even start to double up. So carbon has these 4 places where it can make bonds with up to 4 other atoms. So this is a really big deal. There's a couple important things that you want to know about carbon. I'm going to redraw my Lewis dot diagram. And I'm going to tell you a couple more very important things about carbon. So carbon doesn't really need to gain or lose electrons. And this is really important. It doesn't need to gain electrons. It doesn't need to lose electrons. Yes, it wants to because it wants to fulfill that octet rule, but it doesn't need it. If you get something like chlorine that only has 1 open space, chlorine needs electrons, which is what makes it so explosive or dangerous when you mix it with other chemicals because it steals that electron. On the other side of the spectrum, you have sodium, which only has 1 electron. So sodium really wants to give that 1 electron away. It needs to give that 1 electron away, which is why pure sodium is not something you'd ever find in nature because it'll explode. Don't believe me? YouTube it. Carbon's really laid back. It's okay sharing with anybody. It's not going to steal electrons from anybody. It's not going to try and push its electrons on anything else. So it's pretty laid back. Carbon is small. Because it's small, it can make crazy shapes. You all make fun of Miss Laughlin for being so small, but I can fit into places like the McDonald's play areas that you probably can't at 6 feet tall. So the small thing is actually a good thing in this point because it can make crazy shapes and it can bond in different areas. And because carbon is so laid back, it can bond with many different elements. And that's what makes it so versatile and why we can use it in our bodies so readily. The easiest thing to look at when we look at bonding is going to be methane, which is just carbon and hydrogen. So here's my carbon dot diagram. Hydrogen is in column 1, so it only has 1 valence electron, and these are going to be shared electrons here. This is methane. This is what's in cow farts, true story. And these, where the hydrogen and carbon are sharing, this is called a covalent bond. You remember covalent bonds are sharing bonds. The other type of bond, an ionic bond, would be where the electrons are completely transferred. With covalent bonds, though, we share. Hopefully this has cleared up some information for you about carbon and brought back a couple memories from middle school science for you with how atoms and electrons and protons and neutrons are all structured. If you have questions about this, please feel free to watch the video or any of these videos again. Or if you still have questions and the video is not quite answering it, you can email me or come see me in class. Thank you.